Thank you very much for being here today. Thank you very much, David, for organizing this great event. It's great to be able to talk about consensus. So I'm going to go right ahead. Ledger consensus with dynamic availability. And it's a story touching a little bit from early work I've done regarding the Bitcoin protocol, understanding the properties of the Bitcoin blockchain, and then bringing to the proof of stake protocol of Ouroboros, which has been designed over, or I should say, family of protocols that we designed over a number of years, starting 2016, so 6 years already. So the first talk of the day, so I'll just take also a quick opportunity to say what is consensus. There are a few different variants of the problem, but that's sort of a classical. We have n parties. They have inputs. These inputs are V1, V2, Vn, and they would like to get some output from the protocol. The high-level requirement is that we agree on the output. So they all contribute an input and they agree on the output. Now, what makes this interesting? Some of these parties do not necessarily follow the protocol. They diverge. And classically, the assumption is that we can bound this number of parties by a certain parameter. That parameter is T. Now, this has been sometimes called Byzantine behavior. So the parties are Byzantine in the sense that we have no guarantees about what they do. So this is not a failure of, for example, like they're crashing and they don't send messages, is that potentially they are hacked and they're doing something completely arbitrary. So the properties of the protocol should be defined in the presence of this malicious coalition of parties. It is a coalition because we assume that they all act together. Perhaps they are coordinated by a single entity. And this entity would like to disrupt the process of the honest parties, confuse them. Now, the properties of consensus, there's also a set of different properties here, but these are some pretty standard ones. The output should be defined for all honest parties. That's sometimes called termination. The output of the honest parties should agree. That's agreement. And now there's a few different variants of the other property called validity. That's the first one you see here. The third one from the top basically says that if all honest parties agree on some value, that should be the value of the output. So that's the same value that they should produce once the protocol terminates. And there are a few other versions like strong validity and a few more that have been considered. So that's the problem. Now, this, in a way, it's a sort of more basic problem like the consensus. It's like a one-shot. Parties have some input, they want to get some output, and it's done. Now, in the blockchain setting, and not only, I should say, we're also interested in another variant of this protocol that is actually related to state machine replication, a concept and a class of systems that has been studied since the early 90s. And it's like an ongoing process. In this case, we have clients, they submit transactions, and there is a ledger consensus protocol that makes it feasible for a set of servers to produce a log of these transactions. Alternatively, you can also think that they want to also execute those transactions. Those transactions are requests to process something, right? But let's take now the simplest variant here that basically says, they just want to build a log of all these transactions. Now, there are a few ways to try to define the properties of such a ledger consensus protocol. Observe now, it is different. And it is different because now it's not a one-shot. It's not just a set of parties. They have some inputs. They want to produce some output. It first of all has this client-server structure. Clients submit transactions. Servers create the log. But we have to figure out exactly what they want to do. Now, the first property, you can parallel it to something like consistency. And it's similar in a way to agreement. It basically says if you get two honest servers, the log of one server at a certain time is going to be the prefix of the log of another server at this time or a bit later. There's a small detail here. The fact that if we want to actually this statement to be right, in the right-hand side, we consider not only the log of the server at a certain time, but we also include transactions that are in progress. Intuitively, what this means is that there is a long common prefix there that is created by these servers. And if you query different servers, you will be in this large common prefix. Now, that's like one aspect, consistency. Now, what's the other? We also want this common prefix to have transactions, right? We don't want it to be empty. So it should be the case that if the servers see an input that makes sense to them, and that's what actually you see in the first part of this. So if for all owner servers, they have a transaction that is consistent with their view at a certain time, then if some time passes, and that's, let's say, U steps, let's take sort of a synchronous model here that the time passes, and for all of them, it passes in the same way. That transaction should be in everybody's ledger. So we wait, transaction gets processed. So this captures the two aspects, right? Liveness, these are transactions go in, and then we have consistency, which means that the servers agree. Now, the Bitcoin blockchain, introduced by Nakamoto in 2009, as you, I suppose everyone in this room would know, it is a ledger consensus protocol. Now, participants, the servers, they are called miners, and they run a proof of work algorithm at every step. Now, what's interesting about this protocol is that it's a ledger consensus protocol with some unique set of properties, which, when the protocol was introduced, were a rather unexplored territory for a consensus problem. We have synchronous communication, but no identification of message sources. And there is an unknown and fluctuating number of participants. This, as we will see, relates to this concept of dynamic availability. So the participants do not know how many of them are out there. And furthermore, they cannot necessarily predict how this number will change in the very near future or even in the next step. There is a computationally bounded adversary which possesses 50% of resources, but contrary to the sort of classical way of looking at the problem, we don't restrict the number of servers it has, we just restrict its computational power. The setup is a public random string, and the protocol actually even tolerates small spikes of adversarial majority, and even more, it gives some type of privacy for the maintainers of the protocol. So that's the threat model, like, in a few sentences of this protocol. So let's think a little bit focusing a little bit of this aspect of dynamic availability. The key point is that it enables the protocol, if it is a ledger consensus protocol, to retain safety and liveness under a wide variety of participation and value patterns. And just to give an example here, for instance, if X% of the nodes stop working for any constant X, the protocol still keeps going. And importantly, it gives you both consistency and liveness as long as 50% of the active nodes are following the protocol. There's also this distinction here between active nodes and nodes that are basically not participating at all. And that's like an essential feature of this class of ledger consensus that we get from the sort of Bitcoin approach of looking at this problem. Now, that's interesting to contrast this with the more traditional BFT approach and how this BFT approach has also been considered also in the blockchain setting that takes a different perspective about how to make progress. So the key point in this class of protocols is counting votes. So somehow you have to create like and understand and parse a set of votes. And hence, it is essential to be able to predict participation. Now, something that it's interesting about this aspect is that the more adversarial tolerance we would like to have, the better this prediction should be. Now, and it's interesting to contrast this from what we get from the Bitcoin blockchain as a ledger consensus, where the adversarial tolerance is 50% and it's unaffected by what is the actual participation. So if participation, let's say, is 70% or 30% or 10%, protocol still works as long as the majority of the honest, we have a majority of the honest nodes, or if you want, the majority of computational power. So useful distinction. Now, two problems which are shown in these first 10 slides. And we have consensus and we have ledger consensus. What's the relation? So you might think that this is a very trivial question. If we have a ledger that everybody agrees and does progress, well, it seems to should be pretty trivial to be able to just solve the single shot consensus problem. Everybody shares their input and then we kind of try to figure it out. But there's a catch. And that catch is that we don't have identities. We don't know how many people are there. So how are we going to be able to do this reduction? So this like seemingly very easy reduction is not so simple. So, however, there is a simple way that this can be done. So this is something that we've done back in 2015, proposing this 2-for-1 proof of work technique. 2-for-1 proof of work is, in a sense, a composition method. It takes one proof of work protocol, another proof of work protocol, and combines them together without making it necessary for the honest parties to do double the work or split their work between the left protocol and the right protocol. So it's a fairly generic composition technique. How do we use that in this setting? Well, now the idea is simple. Because we have one protocol that creates a ledger, what we can do is run a continuous process that mines transaction proof of work. So basically, we have proof of work-based transactions continuously. So everybody creates a transaction with their input. And based on that, it is proof of work. We know that the honest majority of those transactions, that the majority of those transactions will be honest. This solves the problem. How? We put those in the ledger. We allow the ledger to extend. And now we run the majority of those inputs. And in the binary setting, we have an answer to the consensus problem. So here's how this reduction works. So what do we learn about consensus, about the consensus problem from Bitcoin? First of all, one observation which is really nice is that we can get a protocol that has subquadratic communication. And furthermore, this can happen with a 50% corruption threshold. Now, it's interesting to contrast this with classical results in consensus literature that say we should have a quadratic lower bound for communication. Now, interesting caveat here, these results are in the deterministic setting. So basically you have, you are supposed to not have an error, right? Our protocol, the reduction we did before, remember it's based on proof of work. So somehow it has this inherent randomness process. So correctness and security are both probabilistic properties. So that's one way that it's possible to circumvent that lower bound. So no more lower bound of communication complexity being quadratic. Furthermore, there is another classic upper bound for corruption that says that even if you have a correlated random setup in the random oracle model, you should not be able to go beyond n/3 corruption. And that's also something that Bitcoin manages to circumvent. How does it manage to circumvent? Is that it is capable of using proof of work in a way to go around this. What happens in this case is that in order to go over n/3, we have to have a PKI. That's needed, right? So in the Bitcoin setting, we do not have a PKI, but we still manage to go up to 50% in a completely different way. Now, this is one class of sort of interesting things that we can point out about the consensus problem. And now another problem is another interesting characteristic is ad hoc participation. So the participants do not need to know how many of the participants actually engage. So you can think of this in the following way. Suppose we parameterize the protocol for n participants, and then someone can choose any subset to just run the protocol. The protocol will still work. Now, this is a feature that is not shared with any other classical consensus protocol. Why is that? In all these protocols, the typical operation is you parameterize them with a certain number, and then like you can tolerate a certain number of corruptions. And these corruptions, of course, can be like tail corruptions, Byzantine corruptions, but a specific number. They cannot tolerate a situation that, let's say, we parameterize the protocol with 100, let's say, parameter for 100 servers, and suddenly only 10 servers show up. So then the protocol is gonna, for example, just block. Not the case for the Bitcoin blockchain. So these are some interesting features of the Bitcoin blockchain, but, well, as you all know, there are a bunch of downsides. And that's the one I say there is not the only downside, but is one that is frequently mentioned and very much discussed about, especially at the time that we're all very careful about the way we use energy. So there is a huge energy expenditure that the Bitcoin blockchain requires. So it is on par with basically a medium-sized country. So one interesting question arises from this, and it is, Is it possible to reduce the energy expenditure? Because ledger consensus protocols, at least the ones we know from the classical literature, they have like a minimal energy footprint. They just, okay, they send some messages, but they don't actually have this feature of using this proof of work process, which is extremely wasteful. Now, something has to give. We cannot just keep everything in the threat model of the Bitcoin blockchain. So the question is what to give up. So let's say we want to focus on these features of subquadratic communication, dynamic availability. So what else does it make sense to give up? And what we can give up is the fact that the Bitcoin protocol has a public setup. So let's instead adopt a private correlated random setup. Now, in protocol design, a setup is what information is assumed by the designers that the servers that run the protocol have at their disposal in a guaranteed way. So the Bitcoin blockchain, it only needs a public random string. This is sometimes also called the setup of a string in the sky. There is a random string in the sky, everybody looks at it, and that's the only setup that is needed. Why Bitcoin needs a public setup is that because it wants to prevent what's known in the Bitcoin setting as a pre-computation attack. So you have an attacker that somehow mines a lot of blocks, let's say a year ahead before the protocol is being launched. Suddenly you start the protocol, and all of a sudden there's a huge fork that reverses the chain. So Bitcoin, that's the reason that Bitcoin needs a public setup. However, there's stronger assumptions we can do for setup. And this classical one is a private so-called correlated random setup. What does that mean? It's essentially a PKI. Bunch of public keys, and everybody has a secret key. Private, because everybody has a secret key. Correlated, because everybody sees an input that is correlated. Not everybody has its own thing. So that's a sort of a key assumption that, let's say, we're willing to do. And this gives rise to what's known as a proof of stake protocol. So, the Ouroboros protocol is a general purpose proof of stake based distributed ledger of transactions. And it has a provably secure design with a versatile framework that we call forkable strings that enables us to argue security for longest chain POS. So it's something that can be used and reused to give formal security guarantees. So it offers dynamic availability and a 50% corruption threshold, in this way matching what we would expect from something that behaves like a Bitcoin blockchain. So I will just give like a very, very quick overview, and then I will just say some of the variants of the protocol that we've designed over time. So the time is divided in epochs. Epochs are divided in slots. At every point, the maintainers determine the valid chain. Slot leadership is determined in some way, for example, using a VRF, a verifiable random function is an important and classic cryptographic primitive. And then blocks are produced based on this publicly verifiable random function evaluation. The system runs in epoch, and once an epoch terminates, a new stake distribution is determined by looking at the transactions, and then you have a new epoch seed, which is calculated in some way so that it's cryptographically resilient. The adversary cannot bias it, let's say, too much. So that's how the protocol works for servers that run in order. And then we have various features and characteristics for the protocol for the other participants. For instance, for participants that are joining the network and they would like to find the right chain, it is possible to use a rule that we call bootstrapping from Genesis that looks at forks and examines the density in the time domain in terms of blocks that these forks have and favors those blocks with higher density. What we were able to prove in this way is that under certain plausible assumptions, it is possible for any bootstrapping client to connect to the right chain. So higher block density is something that can be used for clients to join. Now, there are a few more features here that I think are worth saying. Let me see if I have enough time to mention. We have the concept of input endorser, and this actually fixes a very important problem that has been observed in the context of the Bitcoin blockchain. In particular, the Bitcoin blockchain does not have a robust performance metric. It uses the number of blocks to measure the performance of participants. And the problem is that this can be manipulated. This is also illustrated very nicely in the classic result by now of selfish mining, and using this concept of input endorsers, as we showed in our 2017 paper, it is possible actually to show that the protocol is an equilibrium under certain plausible assumptions about the utility of the participant. Actually, a very interesting observation here that we can also use the same technique to maximize throughput, and that's upcoming work that we should be completing actually anytime now. I'll just highlight also some other results. One interesting observation here is that these proof-of-stake protocols require participants to have access to a global clock. So basically, they have to look at the time, and they have to get a coordinated time. That's a huge assumption if you think about it, and it's very interesting to see if it can be relaxed. And actually, it is possible to relax that, and we can use the protocol itself to facilitate a clock synchronization mechanism. So we can actually drop the global clock assumption. So in that variant of the protocol, we call it Ouroboros Chronos. I'll very quickly also show you two more results. Perhaps you are all familiar that Bitcoin is quite slow in confirming blocks. One reason for that is that you have to wait, let's say, for K blocks, and only then you're going to get an exponentially dropping error in K. That's bad. Like, we would like to see if we can do faster. And something we did in the work that's called ledger combiners, that we show how you can take a number of chains and combine them together in a single ledger, so that it's possible to get constant time settlement with overwhelming success probability. Something about privacy also that I think is worth saying is that we can also make a privacy-preserving version of the protocol that was called Ouroboros Chronos. And this will bring me to my last slide. So takeaways from this is that assuming correlated private setup and erasures, it's possible to achieve all these properties that we can get actually from the Bitcoin blockchain and a few more. Constant time settlement with negligible error, high throughput, and also privacy of maintenance. Now, something that I would like also to say is that there's also other interesting features that BFT-style protocols have. And actually, I would like to say that a very interesting work and a very interesting direction is trying to get best of both worlds type of results. And also something that David and his team, I know, they're working on. It's a very exciting research area. So I want to acknowledge that it's a very interesting domain, trying to get best of both worlds type of protocols. So for those that are interested to learn more about this series of research that I very quickly overviewed, this is head of papers. And with this, I'll just stop. And if there's time for questions, I'll be very happy to take. All right.